Hi, my name is Irene Chen, and today I'll be talking about numerical calculus, specifically ordinary differential equation initial value problems. So, to formalize, we're going to be considering problems. We're going to consider problems of the form y prime of t equals f of t comma y, with the initial condition y of 0 equals y naught. Notice that the input of y could actually be in the space of r to the n. So y of t, is in Rn, and we can just formalize that by defining it as a matrix of y sub 1 prime of t, y sub 2 prime of t, etc., all the way to y sub n prime of t. We can also transform this and just make this equal to f1 sub t all the way down to f sub n of t, which is then equal to our f of t. We also stipulate that we are actually only considering first order ordinary differential equations because higher order problems can be transformed to first order by introducing extra variables. For example, we can use Newton's second law as a example of the transformation that would be necessary, which is converting the second order into a first order by introducing additional variables. MATLAB has a series of very good ODE initial value problem solvers that employ adaptive time stepping, so H is varied during the calculation in order to increase efficiency. As we used ODE 45 in class, we also discussed ODE 23, which simply refer to the number of terms that are used. So, for example, ODE 45 would use the fourth and fifth term, whereas ODE 23 would use the second and third term in order to numerically determine the solutions to these ordinary differential equations. For this video, I'm going to talk about the forward Euler's method, which is one method of solving these types of problems, the backward Euler's method, and then the trapezoid method. The first two are very straightforward. So the forward Euler's method, which we've used in class, simply calculates the next step. So let's say y sub k plus 1 equals y sub k plus h f of t sub k y sub k. This is called an explicit form because you're able to find the next term y sub k plus 1 in terms of the previous terms. Alternatively, the backward Euler's method, as the name suggests, involves you going backwards. So here we're solving y sub k plus 1 equals y sub k plus h times f of y sub k plus 1, y sub tk plus, oh, I messed up. These two should be switched. So f of t sub k plus 1, y t plus 1. Yk plus 1. There we go. Note that this is actually an implicit method because now we have to solve for yk plus 1 given our values as is. The question may arise, why would we ever use the backward method as opposed to the forward method? As it turns out, in stability in terms of the size of the stable regions, implicit methods are often better. Lastly, we'll introduce the trapezoid method, which we could think of as a hybrid of the forward and the backward methods. So in this way, we define yk plus 1 as a function of both the present value and the next value. So we have equals y sub k plus h over 2 f of, f of t sub k, y sub k, plus f of t sub k plus 1, y sub k plus 1. In terms of order of accuracy, we can derive based on our definitions of derivatives that the forward order, I don't know how to go backwards, but the forward, let's just put it in the corner. The forward Euler's method is first order accurate. The backward Euler's method is also first order accurate, And the trapezoid method, because of the combination of terms it uses, is actually second order accurate. Second order. And when we think about what we've learned using how to plot error on MATLAB, if we plot the log-log plot against a second order term, they would both appear linear.